The atom, like we talked about earlier, has protons, neutrons, and electrons. The protons and neutrons are in the nucleus, and the electrons kind of circle around the outside. Now, one thing we're going to see we haven't talked about too much is that really most of the atom empty space. It's kind of like ghost-like. There's not that much there. In my little animation I'm showing right there, the nucleus is pretty big, but what we're going to see here in a little bit is that if I was to actually write down the actual size of the nucleus, it would be like bam. It would be like the smallest dot I could make, all right? So that right there is my nucleus, and honestly, even that is too big for the type of volume there I drew for the atom. We're going to see it's really, really small. Another thing that's really interesting, in a neutral atom, the electrons and protons are equal to each other, all right? And that's going to be important to us here coming up in a little bit. Most of this chapter, chapter 2, part 1, the atoms will be neutral. And if they're neutral, electrons and protons will be equal. The neutrons, not necessarily so, and we'll see that in a little bit. And then finally, each atom is very, very small. All right, very, very small. It says here that a teaspoon of water has 3 times as many atoms as the Atlantic Ocean has teaspoons of water. That's right, it's really small. So first of all, if you have an atom, most of it is empty space once again. You can figure out that in a neutral atom, electrons and protons are equal. The nucleus, super, super, super small in the middle, and very, very small atoms. Just a gazillion around. We'll play with some of those things here coming up. Protons, here's kind of an overview of protons, electrons, and neutrons because we're going to do so much of it. We're going to see that protons, they found had a positive charge. All right, so protons, positive, the P is no accident. The mass of a proton, 1.6726, etc., times 10 to the minus 24 grams. Now, 1 pound is 454 grams. So you've probably seen like a pound of JoJo's or a pound of flour or something like that. All right, this is many, many, many orders of magnitude smaller. So the proton is not just small, it's freaking small. And that's a really unwieldy number to use, 1.6726 blah blah times 10 to the minus 24. So this is the first time we're going to start using atomic mass units, AMU. The proton is 1.0073 AMU. So you can use that AMU number and stuff, which is much better to use than that times 10 to the minus 24 things. And again, an AMU is equal to a Dalton, if you want to say that, that's fine. Electrons are negative, all right? If the protons are positive, then electrons are negative. So a lot of the glue that holds the atom together is going to come from the positive protons being attracted to the negative electrons around it. Now, look at that thing. The relative mass of the electron, 0.0005486. Now remember, that's AMUs. The proton, 1.007 AMUs, and the electron 0.0005. So the electron is really small compared to the proton, all right? They have equal but opposite charges. So the electric charge on the electron is negative and the electric charge on the proton is positive. They're equal in charge, but in terms of mass, how much they weigh, okay? Electrons are super small. It's about 2,000 or so electrons in a proton. Not a little bit less than that, I think, but pretty close. Now, neutrons are neutral, all right? That's N and N, that's easy. They don't have a charge, so they're not attracted to protons or electrons. But I would like you to focus on the mass. The mass of a neutron, 1.0087, and that's more than the proton's 1.0073. So in terms of mass, we would say the neutron is most massive, followed by the proton, and they're about the same. Proton's a little bit less, but pretty close to the same. And then much, much, much less than the proton would be the electron. However, in terms of charge, protons are positive, electrons are negative, neutrons are neutral. put these atomic particles in order of increasing mass. So that means smallest to largest. And like we talked about earlier, the electron is by far the smallest. Protons and neutrons about the same, but neutrons are a little bit more massive than protons. So answer D would be the correct answer here. Now that the protons, electrons, and neutrons were discovered, they didn't know how they fit in the atom, all right? They kind of figured it was a spherical thing, but they weren't totally sure. So the same guy that did the charge to mass ratio for the electron, J.J. Thomson, also proposed what's called the plum pudding model. And plum pudding was a type of dessert, which was really popular in England at the time, I guess. And so this made a lot of sense to a lot of people for whatever reason. In the plum pudding model, which I showed a little picture there, you can see that there are negative electrons, those little blue dots, and the overall atom was kind of a diffused positive charge. All right, they really weren't totally sure on the protons yet, but that's kind of what they thought it was, and that sounds kind of cool. Now, if the plum pudding model would have been accurate, you would have had a relatively large volume, and you would have had negative spheres or negative electrons in the positive cloud of low density. So if you think about a cookie, the little blue dots would be like, I don't know, the chocolate chips, all right? And that's where the negative charge would be, while most of the cookie would be kind of a diffused positive charge. This worked for several years, but Rutherford, who was also the person that formalized the proton, came up with the correct model with a really cool experiment called the gold foil experiment.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
What Rutherford did is he used an alpha particle source, and alpha particles have a positive charge, and he basically fired these alpha particles at a very thin layer of gold. And because gold is used in jewelry and all kinds of things, they could make pretty thin layers of it. And most of the alpha particles went right on through, all right, no problem. But once in a while, all right, these alpha particles would hit that nucleus, and they went crazy. Some of them would go off to the left or the right a little bit. Some of them would come back straight at the detector. And again, what they used was they used one of these photographic plates that Henry Becquerel was using to see, like they would see like little smudges where the beams would come back and hit it. And that's really cool. And no one had done this before. Rutherford's gold foil experiment showed that the atom, pretty low density, but you've got a super dense and positively charged nucleus in the middle of the atom. This is a kind of a better demonstration of what's going on. So these little spheres right here, these are the gold atoms. So in the gold foil, there's not very many of them. And then these little guys right here are going through. Those are the electrons from the, or thanks for playing, the alpha particles that are coming from the radioactive source. And again, most of them just go straight on through. Nothing's happening. All right, I can draw in some here if you want. All right, but they just go straight through. However, once in a while, like this one right here, it comes up and, this one right here, it comes up and bam, runs into the nucleus. And then it kind of goes back, reflects off. Or some of them refract, which means they kind of go to the left or the right a little bit. They go all over the place. Now again, most of the alpha particles straight on through. All right, no problem. But one or two of them did. And so they concluded that, man, most of the atom pretty empty. And this right here is a really good description of what the atom really looks like. All right, you've got a super spherical kind of substance. By the way, look at those distances. Most atoms are about 10 to the minus 10 meters across. But in the exact center, you have the nucleus. And look at this number right here, 10 to the minus 15th, all right? So 10 to the minus 10 is small. 10 to the minus 15th is freaking small. So again, it's like the super small dot in the middle of the atom I was trying to tell you about earlier. So again, when alpha particles were fired through, most of the time they didn't see anything, all right? They just went right on through. But man, once in a while they hit this nucleus, which was supercharged, and because the nucleus is positive from the protons, positive alpha particles, all kinds of craziness. So the alpha particles would refract and reflect and all kinds of stuff around. So again, to sum this all up, gold foil experiment, super important for chemistry. He fired alpha particles at gold. Most of them went straight on through, but some of them like refracted, went off to the left or right a little bit. Some of them actually came right on back to the detector itself. That showed that the atom is mostly empty, and in the very small, many orders of magnitude smaller, is where you have the nucleus, and you've got the positive protons and the negative neutral neutrons inside it. Pretty cool. And that really is the current theory of how the atom's put together, which is kind of neat, still holds even today. So to summarize, protons and neutrons are in the nucleus, and the electrons kind of like circle around the outside. We're going to talk more about the electrons in Chapter 6, so I kind of hedge a little bit and say circle. There's more to it than that, but we'll talk about that more in Chapter 6. Now, most of the mass of the atom is in the nucleus. That's where the protons and the neutrons are. And remember, protons are a little less than neutrons, but they're both about the same, and electrons are like 1/2000, so they're really, really small. So most of the mass, the weight, is in the nucleus. Electrons only have a little bit of the mass. Nucleus is super dense, all right? Because those neutrons and protons are smacked in there together, it's going to be really crazy. We'll talk about that more in the problem set, what's going on. But most of the atom is actually empty. It's almost like ghost-like. The electrons have a lot of volume and not a lot of mass. So most of the atom's pretty mellow, pretty chill. And then finally, I just want to bring up again that an atom is neutral if the protons and electrons are equal. And in Chapter 2, Part 1, that's going to happen most of the time. It's hard for me, even after all these years, to visualize in my mind how small atoms actually are. But fortunately, with modern advances to technology, people have begun to take like home movies and home pictures, if you will, of atoms, which is kind of cool. And this is one of the first ones. This is actually, this little picture right there shows little iron atoms. It's a circle of iron atoms. And earlier I said how roughly an atom is about 10 to the minus 10 meters in diameter from one side to the other. In this picture, the radius of the circle, and the radius is from the middle to the outside of the circle, 71 angstroms. And an angstrom is equal to 10 to the minus 10 meters. Now you can see that the angstrom is an A with a circle on the top. It's kind of a cool unit to write, and that's probably why chemists use it. But anyway, you get the idea. This is actually a picture of these iron atoms all put in a circle. It uses something called STM, scanning tunneling microscopy. It's a technique that's used. There's a website from IBM. You can actually see more information.